Good evening, everyone. Today we are going to discuss about lung cancer prediction. First, we will listen about the introduction about lung cancer prediction. Lung cancer occurs due to the development of large number of abnormal cells, which leads to death in some cases. So, it's really important to predict lung cancer in early stages, which helps in saving lives. Early prediction of lung cancer helps determine the level of diagnosis at which the patient should be treated. With the help of doctors, the medical team, and save money, so it is really important to predict lung cancer in early stages, which helps in saving lives. Early prediction of cancer helps to determine the level of diagnosis at which the patient should be treated with the help of doctors and medical team, and which saves our money. Now we will see the code for lung cancer prediction. First, we have initialized the data science libraries like pandas, numpy, matplotlib, seaborn. For these are used for data manipulation, numerical operations, and visualizing the data. After we have imported the libraries of scikit-learn for model selection, pre-processing, and feature selection, oversampling. These machine learning tools like train test splits divides the data into training and testing. Variance threshold helps remove low variance features. Label encoding converts text labels to numbers, and smooth helps balance imbalanced data sets by creating synthesis examples. Here we have taken our data set and imported it here. Here we have the loaded our data set and done the initialization, checking the size and few for first rows, statistical summary and checking for missing values. Like date like data.info shows our number of features present in it, and data.head shows top 5 features of our data set. Data.describe data is null shows how many null values are there in our data set. As in our data set there are no null values, we continue with our process. From here we start our data pre-processing techniques. This is the code to transform categorical values like gender and lung cancer status into numerical values like two zeros and ones like binary values. So that can be used in machine learning models. Here we have done exploratory data analysis like label encoding. This section examines the distribution of lung cancer in the dataset both numerically and visually with a bar chart. It is important to understand that data is balanced and imbalanced. So the data is not imbalanced, the data is unbalanced, so we balance the data set. Handling handling the imbalanced data set using smooth. Hence the data is split into features X and target variable Y. The smooth is applied to create a balanced dataset by generating synthetic example of minority class. Here we have applied class smooth and balanced the dataset to equal parts to equal balanced the dataset. Outlier detection and error handling. This function identifies outliers using interquartile range method, which robust the extreme values. Here, instead of removing outliers, this function caps them at the 5th and 95th percentile, which preserves the data points while reducing their extreme values. Here we have done our feature scaling. This standardizes the numerical features which have zero mean and unit variance, which is important for many machine learning algorithms. And we have finded our correlation analysis. This creates a heap map showing correlation between all features, helping identifying potential redundancies and important relationships. Here we have done our training and evaluation. This data set is split it into 70 into 70 to 30, 70 for test training and 30 for testing. This code trains and evaluates multiple models like KNN, decision tree, logistic regression, random forest, XGBoost, and naive-Bayes classifier. For each model, it calculates its accuracy, precision, recall, and F1 score. These are the algorithms for every model we have applied in our code. This is a visual representation of our models. As we can see in this, for logistic regression, we have higher accuracy. In this code, this removes the features with low variance that likely cannot contribute to to our performance. We have removed some models which have not contributed more to our project. We have applied LDA for it. This part of code This part of code identifies and removes highly correlated features which is greater than zero point 0.9 correlation to reduce redundancy. From here, we have applied principal component analysis. PCA is used for dimensionality reduction, transforming the original features into smaller set of principal components. The code evaluates model with different number of principal components 5 to 7 and 9, comparing their performance metrics. In-depth PCA analysis components we have analyzed. This analysis this analysis shows how much original features contribute to the principal component, identifying the most influential features for each component. Visualization of our results. Multiple visualizations created to compare model performance before and after PCA with different number of components. Bar chart for accuracy, precision, recall, and F1 score. This is the bar chart for accuracy for all our algorithms. This blue color indicates for accuracy, PCA5 number of components. This is for number of components 7. This is for number of components 9. As we can clearly see, this number of components 7 has optimal number of features. In, in this code, we perform comparison and visualization of our graphs. This creates a single data frame to compare models between PCA with different number of components. This part of code explains the melt function reshapes the data from wide to long format, making it suitable for creating grouping bar charts with Seaborn. These are our visual representations. Here we have analyzed for the components, number of components 5, and I explained the variance ratio as the number of components 5. There are PC1, PC2, PC3, and PC4 and PC5. The most influential feature for each component we have applied. So for PC1, there is age, PC2, allergy, alcohol consumption, wheezing, and chest pain, coughing. These are the etc. And for PC5 and PC7 also we have finded out the most influential features for PCA. This code creates the 2 into 2 grid of subplots for one of the each matrix: accuracy, precision, recall, and F1 score, allowing for each comparison. This function prefers a deeper analysis of PCA components to understand which original features contribute most to each principal component. It is standardizing the features, applying PCA, creating a data frame for loading components. This part of code identifies features which have significant influence on each principal component by using a threshold value of zero point 0.5 for the absolute loading values. And this part of code, this function creates a summary table showing the most important features for each principal component across different values of n components. The summary table is displayed in the format way using the tabular libraries and save to CSV file for further references here. This is a tabular view of a PCA summary table with PCA1, PCA2, PCA3 for number of components 5, 7, and 9. This is the final conclusion of our lung cancer prediction.